How does your brain work? We do know a lot about brains, and by expanding on what we do know, we can deduce even more. Of course, we don't have the complete picture, but this video covers a few actions which are key components of thinking, described in terms of how they are similar or dissimilar to the way a computer works with today's AI algorithms. In a computer, the simplest thing is a bit. A bit can be a single transistor, and it has one of two states. It is either on or off. In the brain, the equivalent building block is the neuron. In the simplest possible model of a neuron, it also has just two states. It is either firing or it's not. If you look at an individual bit within either a computer or a brain, it has no meaning. Bits only have meaning in the context of other bits. In the computer, our bit of interest might be part of a character code in some text, or part of a binary number, or an image pixel. If individual bits only have meaning within the context of relationships with other bits, how do we know the relationship? In the computer, we derive the relationship because bits have addresses. Addresses give bits a sequence, so we can say that bits are in a certain order. Because of this sequence, given the address, we can look at other related bits, like a file name, and find a program which will properly interpret our bit to reconstruct an image, show the text, or add a number, for example. In the brain, there are no addresses. The relationship between any bit and others is defined by physical connections. A neuron might not be connected at all to the neurons which are physically closest to it. In fact, in the neocortex, the thinking part of our brains, neurons can be connected to relatively distant neurons. Without an address, how can we locate information within the brain? By content and by relationship. Your memory includes phrases of speech. If you hear "Mary had a," your brain will find the match and fill in the rest of the phrase. It may also find alternative matches of lower probability. Google is already really good at this, much better than your brain. This function also works with images. In this image, your mind sees a yellow square. In this other image, you also see a square because that is the closest match based on the information given, even though the image is of 4 disks with pieces missing and no square actually exists. Your brain is given a partial input and can return the complete information. Now, let's consider relationships. When you see an object, you can see its many attributes, for example, color or shape. Considering the yellow square, there might be separate neurons in your brain which represent abstract concepts of yellow and square, which would both fire. All yellow objects you know about are connected to the yellow neuron, and all square ones are connected to the square neuron. We can expect the abstract yellow neuron to be connected to a neuron representing the word yellow. The word neuron could be connected to a series of neurons connected to individual letters, so you could remember how to spell yellow. In order to speak the word, you need different information, the sounds or phonemes needed to pronounce the word. If you hear yellow spoken, the word yellow and abstract yellow neurons would fire. When the abstract yellow neuron fires, yellow things spring to mind. With all this connection just relating to the concept of yellow, you can imagine the vast interconnection representing the knowledge in your brain. The interconnection is similar to AI software representing a semantic network, or a knowledge base. An important distinction is that in a computerized knowledge base, nodes are typically given meaning, where in this explanation, they are just abstract bits in the brain. This video has been limited to knowledge your brain already contains and a binary model. In future videos, I'll consider more complex models and the more difficult problem of storing new information in your brain's memory.